Hello students, in this class we will discuss about the working of three-phase induction motor. Before that we will discuss about some important rules regarding the EMF production and flux and current. So here the first rule is right hand thumb rule. So by using the right hand thumb rule we will find out the relation between the current, and this is the current, and as well as flux. This B is nothing but the flux lines or flux. Flux lines are flux. Here this right hand rule used to find the direction of magnetic field due to current element is as follows. So simply to find the direction of magnetic field, so we can find out the direction of magnetic field due to the current. So generally we have to keep in your mind the most important thing. Wherever the current is there, for example this is the current is flowing like this, always around this conductor or current the magnetic field is flows like this. The magnetic field is flows like this. This is the flux lines. So that gives the relation between the current and the flux lines and magnetic field. That's why in inductor always current stores in the form of magnetic field. So inductor related to current and the magnetic field, right? So here right hand thumb rule states that if the thumb of the right hand is thumb of the right hand this is the right hand thumb, in the direction of the current flow it will show the direction of the current flow. Look at here, this thumb is the direction of the current flow. Here look at here, the curl finger shows the direction of the magnetic field. So whenever current is like this curl fingers shows direction of the magnetic field. Same here, current flows here and flux density is nothing but the flux. Simple right hand thumb rule. You can put your right hand is like this, thumb is shows upside, and these fingers become curly. Then the thumb direction represents the current direction and these curl fingers represents the magnetic flux density. This principle is very much useful to find out the relation between the current and the flux. So now our topic is working of three-phase induction motor. How three-phase induction motor is working. So when we are discussing about the construction, in the construction part we will discuss about the stator as well as rotor. Any machine consisting of the three parts, one is the stator, another one is the rotor. So we already discussed in the construction part. Here this is the part we have is the stator. So this part is complete, this part is stator, and this part is the rotor. Look at here, stator consisting of the poles 1, 2, 3, 4, 5, 6 poles, and rotor is the squirrel cage or slip ring. So we are looking at the three-phase induction motor in the top view. So by the top view we will observe all these things. So if you observe here, these are all is the poles. These all are the poles. These all are the poles. Look at here. So how many number of poles here? Number of poles are 6. Number of poles are available here. And so this is three-phase induction motor. We have to give the three-phase AC supply. We have to give the three-phase AC supply. So we are giving the three-phase AC supply to the stator first. Three-phase AC supply to the stator. So this part is the outer part is the stator, and in this three-phase we have three phases. First R phase is given to the one pole, and the ending part is given to this opposite pole is nothing but R dash in this direction, and the ending part after completion of the R dash pole, then you will give into the neutral. Next, here Y current is given to the, so beside the pole of R pole, take it as Y in this form, in this direction, and the ending part is given to opposite pole of this. So we are forming the north pole and we are forming the south pole. How it, the south pole north pole direction is like this. South pole north pole direction is like this, right? Same. Next, in this three-phase connection we have B is also same. B is connected to one pole and opposite is connected as make a south. So we can make north and south poles depends on our requirement. In this I take the 6 poles in order to understand the three phases, but practically it may be number of poles may be 6 or 8 or 12, like this it will be changed, no problem at all. So this is the stator pole construction. This is the stator pole construction. Understand? So when three-phase AC supply is given to these three-phase windings, then what happened to the induction motor, we will discuss in this class. So here the stator currents are stator supply is three-phase supply, you know that supply is three-phase AC supply. Three-phase AC supply means we have three currents. First current is IR, it will be represents IM sin R cos. So in this form I will take the cos omega t, no problem at all. And we have another current, second phase IY is IM cos omega t minus 120, and we have another phase IB, that is IM cos omega t minus 240. And we have another important thing, we are connecting the windings here, we are making the windings here. Windings also connected three-phase winding connection. So stator have three-phase winding connection. That is, the first phase we are connected to, take it as a winding connection is NR, that will be N cos theta. And we have for Y phase we are connected winding like this, N cos theta minus 120. And another winding NB, you can take it as N cos theta minus 240. So we are giving three-phase AC supply to three-phase windings, properly arranged windings. For first winding, there is a displacement between the three windings is the 120 degrees. Understand? And the currents displacement between the three currents is also 120 degrees. Whenever three-phase supply is given to three-phase windings, then we can get, so rotating MMF will be produced. It is represents with the FR. This FR, it is produced in stator, that's why it is called it as stator rotating MMF. rotating MMF will be produced. MMF means magnetomotive force will be produced. Magnetomotive force will be produced across the stator. Magnetomotive force will be produced across the stator. This MMF, rotating MMF will produce the rotating magnetic field. It will produce the rotating magnetic field. This represents with the RMF. It is produced in the stator, that's why it is called stator RMF. It is named as the stator RMF. This represents with stator RMF. This is flux stator RMF. Understand? So the first most important point is, whenever three-phase AC supply is given to three-phase windings, the rotating MMF will be produced. Wherever the rotating MMF is produced, the rotating flux will be produces. Rotating flux means generally whenever we have North Pole and South Pole like this, North Pole and South Pole, the flux lines just traveled from North Pole to South Poles. And here also we have North Pole and South Pole, the flux lines travel from North Pole to South Pole. Here also North Pole to South Pole. By using these three fluxes, a flux will be produces, the flux will be rotates in the air gap. This flux will be rotates. This flux is known as the rotating magnetic field. This flux will be named as the rotating magnetic field. This flux is rotates with synchronous speed in the air gap. This flux will be rotates. The stator RMF, most important thing, this is stator RMF rotates with synchronous speed in air gap. So we have some space is there, that the space it will rotates. So one flux is produced, the stator RMF, that flux will be stator rotating magnetic field will be produced. The stator rotating magnetic field be rotates with the synchronous speed. Here stator is constant and rotor is constant. Only flux is produced, that is rotate with the synchronous speed. And if you observe here, we have the conductors, we have more number of conductors. Generally we have a formula for this FR means rotating MMF. The formula is there. The formula is 3/2 Fm cos theta minus omega t. We have a formula. That formula is FR equal 3/2 Fm cos theta minus omega t. But we don't require that formula in this here. We have a Faraday's law. Now we will discuss about Faraday's law. We have to write a Faraday's law. We have to understand the Faraday's law here. The Faraday's law. We will understand Faraday's law. Faraday's law represents whenever conductor cuts the magnetic field, it induces EMF. Whenever conductor cuts the magnetic field, it induces EMF. Faraday's law states that we have to write the statement first. Whenever conductor cuts the magnetic field, it induces EMF. induces EMF. That means conductor cuts the magnetic field means we have to have an idea. For example, we have a conductor here. For example, we have a conductor copper wire or aluminum wire. This is the conductor, and we have a flux lines, and we have some flux lines. So we are creating a north pole and we are creating a south pole here. Always north pole to south pole flux lines are travels. Flux lines are travels. Whenever the flux is travels like this, but that flux must be variable. That means flux must be d phi by dt. Rate of change of flux is there. Then the EMF is induces. EMF is induced. If it is a AC flux, so not like this, keep it. It is a AC flux. This is the one condition to produce the EMF. And we have another condition. For example, we have a conductor. We have a conductor. That conductor is rotates. We have one conductor. The conductor is rotates. Actually, it is in all rotation. It is in rotation. Flux is stationary. We have north pole and south pole. Flux is stationary means it may be a DC flux. It may be the DC flux. The flux will be travel like this, north pole to south pole. North pole to south pole. In this condition, here conductor is rotates, flux is constant. Automatically, it will induce EMF. In this case, flux is rotation. Flux rotates. What about conductor? Conductor constant. Then EMF induces. In this case, conductor rotates. In this case, conductor in rotation and flux is constant. Then EMF induces. So in order to produce the EMF across any conductor, the most important thing is to produce EMF. Most important thing for any condition to produce EMF, three things are important. The first thing we require conductor, and second thing is we require magnetic field. Third thing is relative speed between both conductor and the magnetic field. Speed between conductor and magnetic field. Then EMF is produced. Otherwise EMF doesn't produces. So that is the Faraday's law to produce the EMF. So here in this condition we have conductors. We have more number of conductors. Just I am taking only single conductor. Just I am taking a single conductor from the rotor, and flux is traveling. Which type of flux it is? Flux in a different color. This is the conductor. Generally it is a stationary conductor. And what is the flux? It's a rotating magnetic field, that is rotating flux. Flux is traveling from the conductor. But what type of flux is? Flux is rotating. And what is this conductor? This is the conductor actually. Conductor is constant. Then what happened? EMF induces in conductors of rotor. EMF induces conductors of rotor. Understand? Conductor induces EMF induces conductor across the rotor. So we have more number of conductors and a lot of EMF is induces, and all conductors are, if you observe here, all the conductors are, one side is short circuit, both sides are short circuited like this. This is the formation of the conductors. Generally these are connected with the end rings. Actually these are connected with the end rings. If you observe the rotor diagram, this model only. So go back to the working of the three-phase induction motor. If you observe here, these are connected, these are slots consisting of the windings are nothing but the conductors. Conductor one side is short circuited. So here as a conductor, a EMF is produced at point E is produced here, and another side is short circuited. Here potential difference is E, here potential difference is 0, then automatically current will be produces. Therefore rotor another side is short circuited, another side is short circuited. Therefore, so rotor currents will be induces due to the short circuit. Rotor currents will be induced. Why it is induces? One side potential difference is E, another side is 0. Rotor currents induces in windings. Rotor currents induces in windings. Understand? So therefore these rotor and rotor windings also three-phase connection. This is also the three-phase connection, and induced currents also three-phase currents only. Why? Supply is three-phase currents. Then what happened? Therefore in the rotor also, rotor currents three-phase currents, rotor windings also three-phase. Therefore rotor also produces rotor windings produces rotating magnetic field, RMF of rotor. First initially stator RMF produces, after that by the Faraday's law rotor also produces rotor RMF. So finally in the rotor winding, in the air gap we have two things. The first thing is, this is the stator flux, and rotor also in the same direction it will produce the another flux. That flux is rotor RMF. First thing is the stator RMF, second thing is the rotor RMF. So look at here, it will produce the stator RMF as well as rotor RMF. So therefore in the air gap we have two RMFs. So this is the stator and this is the rotor. Assume that we have two. First one is the stator RMF, another one also rotor RMF. Right. So we will get, so in order to produce the torque we require the three conditions. So to produce the torque we require three conditions. So first we will write torque production. What is torque? Torque is the twisting force. It is useful to rotate the rotor. So for any torque of the any machine, generally torque production, here we require the three conditions. That is, two rotating magnetic fields RMFs are required and rotates in same direction and same speed. Both are must be rotates with same speed with some displacement. Then torque will be produced. Displacement. So we have two RMFs. One is stator RMF, which is produced with synchronous speed, and again rotor RMF is produced, that is also rotates with synchronous speed. And we have the third point. The third point also, first stator RMF is produced, after some gap rotor RMF is produced. It has some displacement also. Then therefore torque will be produced. By the three conditions is satisfied, then the torque will be produced. So, and torque will be produced on rotor, and this rotor will be rotates in the same direction of RMF. That means if the flux, for example, this is the rotor actually. This is the rotor. You know that this is the rotor. If the stator RMF is in this direction and rotor RMF after some displacement will form, this is also in this direction, then the rotor is also in this direction. Rotor speed also in this direction. So we will discuss the rotor direction by the Lenz law. So to get the rotor direction, we will discuss in Lenz law. To get the rotor direction. So in order to get the rotor direction, we will use the Lenz law. Lenz law means simply Lenz law we can say that effect oppose the cause. And here we will look each and every point. That means what is the cause? Cause is the torque production. What is effect? Effect is generally to produce the torque. What are the requirements? Three things are required. What? First, stator RMF and rotor RMF. Third is the displacement or relative speed. And we have the another cause, that is this is the one type of cause, and we have another cause. Another cause is, and we can discuss in another manner, then you will understand very easily. Generally, in order to produce the rotor RMF, first point is the EMF production. EMF production on the rotor. Understand? EMF induced on the rotor. So the cause is, you can take it as the EMF induced. What is effect? In order to produce the EMF, what are the things? Three things are required. One is the flux, another one is the conductor, third one is the relative speed. This relative speed is the cause, main cause. This relative speed is the main cause. So in order to by producing the EMF, it try to decrease the relative speed. That's fine. So initially initially rotor is like this, stationary, it is stationary, no rotation, and flux is synchronous speed. Flux rotates with the synchronous speed, and in order to decrease this relative speed, send the relative speed between the flux and the flux is synchronous speed, rotor is 0, then ns. So in order to decrease this ns, the rotor must be rotates in the same direction. The rotor must be rotates in the same direction. That's why induction motor rotor, in the induction motor rotor rotates in same direction, same direction of the flux. That means stator, that means RMF, as well as rotor RMF, stator RMF and rotor RMF. So this is the cause for the relative speed, cause of the in this case. So I think you understand the working. Simply we are creating the flux and we are giving the electrical supply to the stator, and that electrical supply is entering into as a flux into the rotor, then that will be converted into the mechanical supply, then the rotor will be rotates, okay. But in order to rotate this, we are creating the stator magnetic field, stator RMF, and creating the rotor RMF, and we are creating the a displacement between this, then the torque will be produced. So by using the torque, the rotor will be rotates, So in the next class we will discuss about the continuation topic of this. Okay, thank you.